Hi, Year 12. Right, another week, and I've got another practical to measure Planck constant for you. It's quite easy about this one. So let's see what sort of value for H we get with some LEDs. Right. So basically, this is it's another practical to find the Planck constant, but this time I'm going to use different coloured LEDs, and it's actually something that you can build at home if you had access to five different coloured LEDs and a voltmeter. It's that simple. Anyway, this is, if you remember from when we studied electric circuits, the IV graphs, you should know the IV graph for a fixed resistor, a filament bulb, and a semiconductor diode. Right, the diode is the quite interesting one in the fact that when there's a negative potential difference, there's zero current. Okay, and that's why they only let current flow in one direction. So they have to go above a certain voltage first. Though this is not a little anomaly on the graph. This all semiconductor diodes do this. Okay, the voltage, the positive voltage, has to reach something that's called the threshold voltage. Okay. Before that, anything below the threshold voltage, again, we've got no zero conduction. After the threshold voltage, the diode will be a roughly ohmic conductor. Okay. So, but this is the important thing today. It's the threshold voltage. Now, the interesting thing about the threshold voltage for different colored diodes is the threshold voltage is a different value. This value at which the diode starts conducting depends on the color of light or the wavelength or frequency of light. Because don't forget, semiconductor diodes are monochromatic. That means they give out one color of light, they give out one frequency of light, pretty much like a laser. Okay, so all different colors, like here we've got red, blue, green, um, um, yellow, and this will be, I think, a yellow color as well. They're all going to be monochromatic, giving out one frequency of light. Anyway, this is the important relationship. Okay, this is the important relationship here. The longer the wavelength, the smaller the threshold voltage. Hopefully, you can see that. Now, as the wavelength decreases, as the frequency of the light given out from the LED increases, okay, as the frequency increases, we can see the threshold voltage increases. And this is what we're going to use to find the Planck constant, because if you remember this, we did this at the end of electric circuits. We started to look at semiconductors in a bit of detail. Now, if you remember, it's all about the conduction band and the valence band. Right? With metals and conductors, the valence band and conduction band are always overlapping, which means that some electrons in the outer shells can always conduct. With insulators, there's a big gap. Now that gap cannot be crossed. Okay, it cannot be crossed unless there's an extremely high potential difference across the insulator, and then we get something called electrical breakdown. But anyway, semiconductors are slightly different. The gap is just short, is actually small enough for some electrons to get across, and once they're into the conduction band, they conduct. Okay, and semiconductor diodes work like this. Now, let's have a look at the theory. Let's have a look at the maths. Okay, now at the threshold voltage, an electron will just make it across the gap, but then it will fall back down again and emit the energy it got in the first place as a photon. Okay, so the energy gained by the electron from the potential difference is, well, work equals charge times voltage. Work equals charge times voltage. The most important equation in A-level physics. I say that every time. Anyway, right, so the charge times the voltage. charge on an electron is E times threshold voltage Vt. Now that's roughly equal to the photon energy that's given out, because this energy is gained, this electrical energy is gained, but then it's lost again by the electron when it drops back down, and it's given out as a photon. Okay. Now in reality, there's some energy lost. There's some energy lost at this junction, this process. There's some energy lost. So there's a little constant. There's a little bit added here. Okay. So we can actually rearrange this equation to get, okay, let's go down to the bottom one. So we've got the threshold voltage is equal to H over E F plus a small constant. Now, what I want you to do in this practical is, like I said, I've got a range of 5 different LEDs. So we're going to be changing the frequency of light given out from the LED, and we're going to be measuring the threshold voltage for each of the 5 colors. But there's a slight change here. Don't want you to plot threshold voltage against frequency. I'd like us to use values of wavelength in the graph. So let's just have a little look at what we're going to do here. Remember, speed of light is f lambda, isn't it? The wave equation. So rearranging that, we've got frequency is speed of light over wavelength. Right, I want you to substitute for this. So we've got threshold voltage is H over E multiplied by C over lambda plus a constant that we don't know. Now, one last little tweak is just rearranging the H over E and C over lambda. I prefer it like this. We've got HC over lambda multiplied by 1 over lambda. That's not 1 over lambda, is it? Apologies. HC over E multiplied by 1 over lambda plus the constant due to the small energy losses. Now, what are we plotting? Okay, what are we plotting? Should be fairly obvious now. Vt is on the y-axis. Now this is what I want you to plot on the x-axis, which means that this fell here, Hc over E, is the gradient. Now H is the Planck constant, C is the speed of light, and E is the charge on an electron. So if you know the gradient, we've got a value for C, we've got a value for E, we can find the Planck constant. Should be fairly straightforward. So the graph, this is what you're going to plot. We have, it's very similar to the photocell one, okay? But we're not going to be plotting stopping potential. We're going to be plotting the threshold voltage, okay? And we're going to have this constant is a positive value, so it's going to be looking something like that, isn't it? Where the gradient equals Hc over E. Okay, but we're not plotting frequency on the x-axis. I want you to plot 1 over wavelength. Okay, here's your table. This is a piece of kit we're going to use. So you need a video. I'm going to video myself in a minute. You've got the 5 different colors of LEDs. It gives you the wavelengths, and you just adjust this until this is just giving out the first photons of light. Yeah, you drop the voltage across the LED until the LED just starts to conduct. Okay, so that's the pretty neat piece of kit there. Table of results. This is for you to fill in as well. I've got a Google Doc for you. Right, this is important. Okay, we've got wavelengths in nanometers. Now 1 over wavelength. Okay. Remember what I said about in the previous video about tables with very large and very small numbers. I want these values here to be 10 to the 5 m to the minus 1. The reason is when we come to plot it in Desmos, like I said in the previous video, plotting really, really small numbers against normal numbers in Desmos makes it impossible to find the gradient. Okay, so values of 10 to the 5 m to the minus 1 for your 1 over lambda, please. And that should give you a pretty nice graph in Desmos. Right, have fun. Next video for you to watch is me playing with this piece of kit. Thank you very much.